At this point, we've developed some powerful methods to describe particles and systems of particles as they move through space. Linear motion, curved motion, doesn't matter, we can handle it. But what about systems that stay in the same place but still have a lot of motion worthy of describing, like a ceiling fan, or a ball spinning on your finger, or a sleeping yo-yo? In this lecture and the next, we'll address this rotational type motion and develop rotational analogs to the linear equations and concepts we've already covered. Velocity and acceleration will become angular velocity and angular acceleration in the rotating world. Our constant acceleration equations and linear kinematics become constant angular acceleration equations and angular kinematics. Kinetic energy becomes angular kinetic energy, and in the next lecture we'll talk about work, something called torque, and angular momentum. First we'll start with the basics, just like we did with linear motion, angular velocity and acceleration. For the purposes of this lecture and the next, we'll be talking about rigid bodies for simplicity. In reality, bodies can deform in many ways that complicate the situation. They can stretch, twist, compress, etc. We'll be treating bodies as rigid bodies, which means we'll assume they have a perfectly definite and unchanging shape and size. We've actually been doing this all along with everything except for springs. Say we have a speedometer needle rotating around a fixed point at the center of this gauge here. You might be wondering why this couldn't be described with the tools we already have, by, say, picking a point P on the body and analyzing its x and y coordinates as it goes around. And truth be told, you could do this. It just turns out to be quite a chore. Instead, let's focus on the fact that the needle makes an angle, theta, with the x-axis that describes its current position as it spins, because the base of the needle is fixed at the origin and the rest of the body rotates around this point. So we can simply use theta as a coordinate for rotation, so long as it's rotating around that fixed point. Positive theta means the body is spinning in the direction we've defined as positive rotation, and negative theta means it's spinning in the negative direction. We'll be using radians to measure the angle theta instead of degrees because it keeps the relationship between angle and distance as close as possible. 1 radian, or rad for short, is equal to the angle subtended at the center of a circle by an arc with a length equal to the radius of the circle. And I'm going to draw that out for you. So, if we have a circle, do my best here. That wasn't half bad. And here's the center here, here, and here. So if this is R, same with this, and this is S, S is equal to R when this angle is 1 radian, 1 rad. So S is the arc length, right? And so therefore we have the expression that theta is equal to S over R. Or, a sometimes more useful version of writing it is S is equal to R theta. So, if you're converting between degrees and radians, you can use various conversion factors. Like, there's 360 degrees for 2 pi radians. 2 pi is all the way around the circle, as is 360 degrees. And so we can say 1 radian is equal to 360 degrees divided by 2 pi. And so 1 radian is about equal to 57.3 degrees. And so thereby, 180 degrees with the same conversion factor, so there's 360 degrees per 2 pi. You could also go 180 down here for 1 pi on top. But this would tell you that 180 degrees is pi. And then, likewise, 90 degrees is pi over 2. And if you're familiar with your trigonometry, this comes as no surprise. You're used to working in radians, but it's a nice review here. Because with rotational motion, we're going to be working a lot in radians. If regular velocity is the amount of distance covered in some time interval, then angular velocity must be the amount of angular distance, or arc length, covered in some time interval. Since we're using the angle theta to describe the position of a rotating body, angular velocity is the rate of change of theta with respect to time. So we use a new symbol, omega, to describe angular velocity. And that's just equal to d theta dt. So this isn't exactly a W. I don't know, my W would be a little different. It's like a really rounded out W. You can look up omega if you like. With linear velocity, we denoted the direction of the velocity with a subscript, like v sub x. For angular velocity, the direction of the velocity is, it's kind of odd, along the axis of rotation, and it's governed by the right-hand rule. So if you have something that, let's see if I can draw this. If you have something like a gear, and it's spinning around this way, I wonder what that looks like for you. Yeah, spinning around this way. So it's coming out at you here and away from you there. And the axis of rotation is going right through the center of it. Then you would use your right-hand rule, and I can't show this very well, except for maybe drawing it. Oops. You'd use your right-hand rule, and you would wrap it around, so your fingers curl around in the direction that the gear is turning, and your thumb should be left pointing upwards. And that is the direction of the angular velocity, upwards. If the gear was spinning the other way, so it's spinning this way, and we still have this axis going right through it that is rotating around. And now, if you use your right-hand rule, you're wrapping your fingers around this way, and if you're using your right hand, then your thumb should be left pointing downwards, and that's the angular velocity direction if it's spinning that way. You gotta make sure you're using your right hand. So no matter what, if our speedometer needle was rotating the xy plane, that drawing at the beginning, then the direction of its rotational velocity is along the z-axis, right? So if this guy is, let's say it's spinning this way, and using our right hand, this axis here, and its angular velocity is into the board there. Not sure if you can tell exactly, but I've drawn an arrow there. Maybe you can, maybe you can't. Yeah, so it's along the z-axis because this was the xy plane. Maybe that helps. All right. So angular acceleration then is the rate of change of angular velocity with respect to time. So we just take one further time derivative. And for that, we use the Greek letter alpha. I'll go to pink here. Alpha. And that's equal to d omega dt, which is equal to the second derivative of theta with respect to time. There it is. And I guess I can go ahead and box this one in too. There. All right.